So welcome everybody to this week's Quantum Theory of Fields, Methods and Strings seminar. This week we have Niccolò Cribiori from KU Leuven, and he will talk about scale separation to us. So thank you, Niccolò, for accepting our invitation. So you can begin whenever you want.
Yes, so thank you for the invitation. It's my pleasure to have this chance to present my work here. And I will try to give an overview of some recent work at the end of the talk and some less recent work towards the beginning about this general topic, which is scale separation, which I think is interesting, especially in string theory and string compactifications. So I think scale separation is a problem which is easy to motivate also for a non-expert audience. And the basic question is actually very simple: are there extra dimensions in our universe? So we know that our universe looks four-dimensional up to very small scales, but still it's a logical possibility that could be extra dimensions, and there is no, in principle, no obstructions in quantum gravity. In fact, some theories of quantum gravity are using extra dimensions, like string theory. Then a more physically oriented question is, what is the scale, the typical scale, which is characterizing this extra dimension? I will call this the Kaluza-Klein scale in the rest of the talk. There is no precise answer as of today, but one can try to give bounds. And for example, in a very crude approximation, if one is only looking at experiments from particle physics, for example, colliders, one might say that since we don't see any new physics at LHC, for example, then this gives us a bound on possible extra dimensions, which could be some order 10 to the minus 18 meters. Maybe one can improve this estimate, but this is not the point here, just to give some rough approximation. If one looks at gravitational physics, for example, from torsion balance experiments, I think upper bound are of the order of the 10 to the minus 6 meters. On the other hand, if we look at our universe, our four-dimensional universe, the size of the observed universe, what one might call, or what I will call for the rest of the Hubble length or the Hubble radius, is a sum of some 10 to the 27 meters, again, as an order of magnitude. So I'm not really interested in the precise numbers, but in stressing the fact that there is a huge difference between this number for the Hubble scale, so the size of our universe, typically, and the putative size on the extra dimension, actually an upper bound on the size of the extra dimension. Extra dimensions can be even smaller than these numbers I put on the slides. So there is a huge gap between these two numbers, no matter how we look at the problem. This gap in physics, in theoretical physics especially, is called a hierarchy problem. So hierarchies refer to the difference between these two numbers. And in particular, in this case, is what people call the scale separation problem. So it's the problem to explain why the ratio between the Kaluza-Klein scale and the Hubble scale in our universe is so small. Of course, in our present understanding of string theory and quantum gravity, we cannot be much more precise than this. So we'll do a very first and naive approximation. I will just ask myself why this number is so parametrically small. Eventually, in the future, people might be able to put more precise numbers here, but I cannot do this at present. At present, I can just ask the question of why the Kaluza-Klein scale is so much smaller in our universe, and can I obtain this in concrete models in quantum gravity and string theory more precisely? So what is the problem now of scale separation when I'm thinking in terms of string theory? String theory is a theory of quantum gravity which is better understood in 10 or possibly in 11 dimensions. So we have along this line, we have extra dimensions. If we do believe that string theory describes our universe, it describes also extra dimensions. The problem is then to hide these extra dimensions. And there are, I think, at least two main lines of research, two main possibilities. In the first case, one assumes that extra dimensions are large but unobserved, or dark in jargon, for various reasons, and I'm not going to go into the details of this line of research. And usually these kind of scenarios are called brain world models. The other case instead is in which extra dimensions are small and typically compact. And this is the case on which I'm concentrating on. Let me just stress that this is not the only possibility. So what I will be talking about is really only the second case, but is not the only possibility on the market. Still, I will concentrate on this for this talk. This second case, when extra dimensions are small and compact, is called more precisely a string compactification. What does this mean? It means that our space-time configuration is some four-dimensional external, is called external space, is non-compact. Ideally, this should be a quasi-de Sitter space to describe our universe. It's not clear if how can we have quasi-de Sitter in string theory today. This is why I put a question mark, but ideally, in a long-term goal, a long-term research, the goal would be to find a quasi-de Sitter four-dimensional external space in a string compactification. And there is then a companion part, which is six-dimensional or seven-dimensional, depending if we start from 10D or 11D. This space is called internal space, is compact, is assumed to be compact. And then the question is what geometry is characterizing this space. Depending on the geometry, I will have different effects in the four-dimensional part. There are, I think, the best understood examples are among those I reported in this slide. So, for example, a four-dimensional Minkowski space type Calabi-Yau. So if I study string theory on this kind of 10-dimensional space, this is one of the best understood examples in string theory. Another case is anti-de Sitter five-dimensional space times a five-dimensional sphere, or ADS4 times S7, or also ADS7 times S4, I didn't put it. These are examples of string compactification, so non-compact space and a compact space, which are very well understood. However, scale separation, especially for these two kind of space, there is no scale separation. What this means, it means that this typical size of this space is of the same order as the compact space. So these spaces are really 10 or 11 dimensional. I cannot think of this as a four-dimensional theory or a five-dimensional theory in a large non-compact space and a small internal space. This is not the case for these two spaces. For Minkowski, it can be the case. I mean, the scale separation, if you look at the definition I gave you before for Minkowski, is a bit more subtle because this thing is infinite in principle. So it will be automatically scale separated. But then this kind of setup has other problem phenomenologically. For example, this would preserve supersymmetry and is not really a realistic setup in any case. So in string theory, then, scale separation is a feature that must be present in string compactifications to explain or to link string theory with observations. There are some comments before going on I would like to give in order to motivate and to phrase better the problem in the more general context of string compactification. One thing which I will mention also later on is that the compact space has to be small, as I was stressing, but there is also a concurring effect. It cannot be too small in a certain sense. Otherwise, we enter a technical problem. The fact that we lose the validity of the approximation in which we can understand string theory. So we can understand string theory at present, at mostly classical, I would say, so in what is called the supergravity approximation, which is a low energy effective approximation of string theory. This approximation breaks down whenever I have scales in my theory which are comparable to the string size, to the string length. In particular, if the Kaluza-Klein scale, so the size of the internal dimension, becomes comparable to the string length, then the supergravity approximation of string theory is not valid anymore and should take correction into account. And this can be typically very hard. So whenever you enter this regime, typically we have to step back because we don't know enough string theory, unless in very particular cases, but in general, we don't know enough string theory to proceed. Another problem, if you like, or open problem, I would say, related to scale separation is what people call modular stabilization. So how this appear in relation to scale separation is really because we are doing a string compactification. So there is a compact manifold, and the compact manifold comes in string theory with typically a lot of scalar fields in the four-dimensional in the external effective field theory. These scalar fields can be exactly massless or can have a mass which can be small. If they are exactly massless, they are called moduli, and somehow are parameterizing the way in which this internal compact space can oscillate and move and can change the shape and the form. The problem arises again whenever we want to match string theory with observation. At present, we see just one scalar field, while, for example, in type 2A, in type 2 on Calabi-Yau, in type 2 string theory compactified on Calabi-Yau spaces, we can have different order of magnitude, like 10 to the some order of magnitude difference with respect to one is not really one, is parametrically different number. So we have to give somehow a mass to these scalar fields in order to explain why we don't see them. So the logic will be that we don't see them because they are so massive that we cannot really probe them with experiments. The problem of giving a mass to these scalar fields, which are accompanying a string compactification, is called the problem of modular stabilization, and is in some sense not unrelated to scale separation, even though we'll not really talk about modular stabilization, but is to phrase the problem of scale separation is in a more general context. So to summarize, then, scale separation is an open problem in string theory. It's not clear in general how to get scale separation in string theory as of today, and it's an open problem which is connected to other open problems in string theory. So it's an interesting problem in this sense. And especially it's interesting for string phenomenology, so to connect string theory to observations, because it's a necessary condition, not sufficient because we need more, but it's like a minimal requirement for string phenomenology. At least we should be able to explain why we observe only 4 large extra dimensions and not more. So the talk will be then structured on this problem in 2 different parts. In the first part, I will give you some arguments as of why scale separation cannot occur in certain string compactifications. And then on the more positive side, I will try to understand in which cases instead scale separation can be obtained in string compactifications. I will stress it again, but let me stress it even now that in both cases, I will not be able to give like a theorem or a definite proof of something. There will be always assumptions, and there will always some corners which are not covered by the argument I give. Okay, any questions, or I can proceed with the first part? Okay, I will then proceed. So in the first part, actually, to be more precise, I will not, as I was saying, will not rule out in general scale separation, but I will do it under assumptions for certain models which are not realistic. These will be models in at least 4 non-compact non-compact space-time dimensions, and with at least 8 supercharges. Okay, so these will be supersymmetric theories with a certain amount of supersymmetry, which can be not minimal in 4 dimensions. And also we'll discuss the 2-dimensional case separately because it's a bit different in the discussion I will propose. In the second part, I will provide instead concrete constructions, possibly in string theory, in which scale separation can be obtained. However, these constructions are not today established as string backgrounds. I will explain what this means. Basically, it means there are assumptions and approximations which we still have to understand better if we can trust them or not completely. And in any case, again, there will be really not phenomenologically realistic. So in any case, I think it's fair to say that we can assess the problem of scale separation not in phenomenologically realistic situation yet. So let me start then from the first part. How scale separation is hard, why scale separation is hard to achieve. I will proceed bottom up. And the second part instead will be what is called top down. Bottom up means that I will start from a 4-dimensional or 5-dimensional effective field theory. I will supplement it with some input about quantum gravity, and I will see that this input forbids scale separation. So from the bottom up, a condition for scale separation is basically the fact that the Hubble scale and the UV cutoff, their product must be parametrically bigger than 1, means that there is a gap between the UV scale and the IR scale, and I have a good effective field theory that can live in the between. If this gap is too small, there is no space for the effective field theory to live, basically. This is the rough logic. Okay, this is a standard requirement for effective field theories. What else we can add to this? I will add one extra input, which is the fact observed in nature that gravity is the weakest force. For example, this is true for any of the other forces we observe. For electromagnetism, we can see that the hierarchy is some 10 to the minus 43. So we have an hierarchy here, and the hope that this hierarchy might tell us something about the hierarchy in scale separation. So the fact that gravity is the weakest force has somehow been encoded into a principle of quantum gravity, which goes under the name of weak gravity conjecture. If you are familiar with the so-called Swampland program, this is one of the pillars of the Swampland program. I would say the Swampland program is a famous statement. It's something which people strongly believe to be true, at least in the simplest cases. And for what I need here, the formulation of the conjecture is what that I will use is so-called magnetic formulation. So there is an electric statement and a magnetic statement. I will use the so-called magnetic statement, which is the fact that in a effective field theory of quantum gravity with a U1 gauge coupling, so an abelian gauge coupling, which I'm calling G, the cutoff of the effective field theory is not really the Planck mass, as you would naively expect, but is lower than the Planck mass by a factor of G. So you just have to remind that the UV cutoff is upper bounded by the gauge coupling in Planck units. This is all the information you need. Then I will show that this only information with enough supersymmetry is strong enough to forbid scale separation. And this will be done regardless of the UV completion. So I will just assume supergravity plus weak gravity conjecture, and I will not really give any details of the microscopic string theory model. If there is one model, then the consequence is that this model is not scale separated. Yes?
Can I ask a question?
Yes.
When you say regardless of UV completion, do you think about the possible flux compactification or non-geometric backgrounds that can arise from which can give this effect? Okay.
Yes, so the logic is the following. I just need a 4-dimensional or a 5-dimensional supersymmetric anti-de Sitter vacuum with enough supersymmetry, with at least 8 preserved charges. I don't care if that vacuum is realized in string theory or not. It might be realized. In that case, I would say that that vacuum is not realized in a way which is compatible with scale separation, is not scale separated. If it is not realized, okay, there is nothing to talk about already because it's just a theory which is not theory of quantum gravity.
Can I also ask a question?
Yes.
I didn't understand the difference between the electric and magnetic.
Yes, I didn't mention the electric statement. The electric statement is a statement about the spectrum of the effective field theory. There should exist at least one state in the theory with a mass which is smaller than a number times the gauge coupling and the charge under this abelian statement, under this abelian symmetry. I'm not using that statement. There is somehow a dual statement, if you like, which is the magnetic statement, which is the one I'm showing here.
I see. And so, you mentioned like it was bigger than the magnetic charge. If it's equality, is it like a BPS? I mean,
yes,
you have
precisely.
BPS case, and then if you go up, you have
the BPS case
frame
is typically precisely the BPS case is typically the saturation of the electric weak gravity conjecture statement. Yes, the mass is equal to the charge. Yes, but the electric statement is a statement about the spectrum of the theory. The magnetic statement is a statement about the UV cutoff of the theory. So they are a bit different in this respect. And I would need a statement on the UV cutoff.
Okay, so when you say like the spectrum of the theory, you mentioned like the line operators, right? Like whether you choose the Wilson loops or Tufts loops, or is it something else?
Just more basically a statement about the spectrum content. In the theory, to be consistent, there should be a particle with a mass which is less or equal than the charge.
I see. A dynamical particle fluctuating.
Yes,
Okay.
a state, let's say, yes. Okay. This is what I mean, yes. If the state is not there, then you violate the electric weak gravity conjecture. Yes. Okay, so how does this work? To understand it, I'm proposing first a toy version of the argument, and then I will give a sketch of the complete argument. The toy version is probably more understandable if you are familiar with 4D n equal 1 supergravity. If you are not, please ask me about the details. I will try to explain it as simple as I can. So 4-dimensional n equal 1 supergravity is a theory which is, I think, well understood. And in one of the simplest cases, you can just have one vector field. Okay, we need a vector because we need a gauge coupling. So we have to have vectors. And let's consider just the case with one vector and one gauge coupling. The theory is well known, well understood how to formulate the theory. It is also known that there is a deformation of the Lagrangian, of the effective Lagrangian, which preserves supersymmetry and which is proportional to the gauge coupling. This is what is called a Fayet-Iliopoulos Fi term. Okay, this is a deformation you can add to the Lagrangian. It will preserve supersymmetry on the Lagrangian level. And psi is a deformation parameter. Okay, it will give, in this very simple case with no scalar fields, will give a positive cosmological constant. Now, you start from this, and the idea is to implement a bit of quantum gravity information. First thing you can say is that there are arguments telling us that psi, if it has to be realized in quantum gravity, it must be quantized. You can think of this like some flux, or if you're familiar with string compactification and so on. But anyway, it has to be quantized, meaning I cannot smoothly go to the limit psi going to 0, because this will violate any form of quantization. Psi quantized means there is a lower bound of psi, which is different than 0, is parametrically different than 0. So the only way I can have to turn off the deformation if psi is quantized is to turn off the gauge coupling smooth. If I do this, I'm basically restoring a global symmetry because I'm setting the gauge coupling to 0. This is believed to be problematic in quantum gravity. So there is a conjecture which is saying that there should be no global symmetries in quantum gravity. In this case, I would conclude that the model, the Fayet-Iliopoulos model, in this limit is problematic. You might say, okay, but who is telling you to take the limit? Maybe it's just your fault because I took a wrong limit. Fine. This is where the weak gravity conjecture enters, because the weak gravity conjecture allows me to say something about the model away from the limit of weak coupling. And this is really because, in this case, since psi is quantized, we can forget about it. You put it to like 1 or any number you like, but it will not change. The only parameter you have is g. And g, if you use the weak gravity conjecture, is basically the UV cutoff, is upper bounding the UV cutoff. Instead, if you use the fact that in the sitter, the vacuum energy is a good approximation of the Hubble scale, then you reach an inequality of the type that the Hubble scale is actually bigger than the UV cutoff. And this is exactly against the hierarchy I wrote here. This is really in the other direction. You find precisely a strong violation of this property, which is needed for IFT. So a good effective field theory would not be this one. This would be not a good effective field theory if you impose the weak gravity conjecture as a cutoff. So you would conclude that with enough supersymmetry and weak gravity conjecture, pure Fayet-Iliopoulos terms, so this model is so-called in the swamp. It means it's not a consistent theory of quantum gravity. Now, here I was not really talking about scale separation, even though the problem is much related to scale separation. I will use the same logic now to really constrain scale separation in anti-de Sitter in a much more general setup.
Can I ask something, Niccolò?
Yes.
Can we think about this as the D term? For example,
this is a D term, yes. Is
yes.
The simplest example of a D term for the n equal to 1 supergravity, yes.
Okay.
Precisely.
Okay. Thanks.
You can have more complicated examples with scalar fields, and in that case, you can possibly evade this argument I gave. But for the pure case here without scalar fields, what is called a Fayet-Leopolds D term, you can run this argument very cleanly, I think. Okay, now, what has this to do with scale separation? I can play a very, very similar argument and rule out scale separation in ante-de Sitter vacua. Now, the reason I need ante-de Sitter is because I need supersymmetry to be preserved, so de Sitter will break supersymmetry. I need ante-de Sitter, so I can only look at ante-de Sitter vacua, what I call ADS. And here I'm sketching the argument for 4D or 5D supergravity, and I will comment on extensions later on. Now, a general fact about supersymmetric ante-de Sitter vacua is that the vacuum energy is basically the gravitino mass. Okay, this is a fact of supergravity. Now it comes the point where I need supersymmetry really to run the argument. The logic, I want to impose the weak gravity conjecture, so I need to have a gauge coupling somehow. So at this level, I don't see any gauge coupling. To see the gauge coupling, you have to trade the gravitino mass with some gauge coupling. And this can be done in general, in full generality, with at least 8 supercharges. You can also do it with 4 supercharges, so for the n equal 1, you can be able to do it in some cases, but not in general. I want to have a completely general argument, and then I need at least 8 supercharges. At least I don't know how to do it for the n equal 1 supergravity in complete generality. This is because of a special property of the geometry of the scalar manifold. It means that morally I can write the vacuum energy as minus the gauge coupling square. Now, to be really precise, the weak gravity conjecture is formulated on an abelian group, okay? So we need to understand what is the gauge group associated to this gauge coupling if there is an abelian factor. And it turns out that we can do this in complete generality again. So these people are telling us how a general gauge group breaks down on a supersymmetric ante-de Sitter vacuum in supergravity, in 4D and in 5D. And it splits into 2 parts, one which I'm calling HR and other HMAT for matter. R is for the R symmetry, so it's a symmetry you have in supergravity theories. The important point will be this HR, and we're in a likely situation in which these people are telling us actually what HR is. Okay, so it's SON in D equal 4, where N is the number of supersymmetries. For example, for n equal to 2, will be SO2, so U1. Or in D equal 5, you have these other groups. Now, HR will be gauged by one combination of the vector fields in the theory, which is called the graviphoton. Okay, it's a supergravity name. And the other part will be gauged by an orthogonal combination. These are what people sometimes call the matter vector fields, okay, matter couplings. Thanks to special properties of the scalar manifolds, I can split the full thing, the full gauge coupling, in a similar way as the splitting. So there will be a contribution from the R symmetry, from the graviphoton, plus a contribution from the matter part. But there is no mixture. There is no mixed term. Okay, this is the crucial point. It means I can write an inequality. I can just forget this term and I write an inequality. I take the absolute value, flipping this sign, which I'm here. I know that, again, this is somehow giving me a measure of the size of the external space, like the ADS radius. On the other hand, once I'm here, I can enforce the weak gravity conjecture with respect to this guy. For example, for n equal to 2 supergravity, this would be really U1. I'm really well motivated in using the basic formula for the weak gravity conjecture, so I reach the same formula as before for the Fayet-Leopolds term. This model will violate the hierarchy I gave you here for a good effective field theory. It means physically that my vacuum energy is already hitting the cutoff. There is no window between the vacuum energy and the cutoff. This window has collapsed. So this model is immediately seeing the cutoff. So either this model is inconsistent, and that's it, or this model is basically immediately seeing the extra dimension of the same scale as the model is probing. So the only way to save this model would be to admit the existence then of extra dimension of the same scale as the scales of the model.
Niccolò, there's a question in the chat asking what is S in front of U?
S is it means determinant equal 1, like you have ON or SON, and here is the same UN or SUN. I put it in brackets because this only for n equal 8 supergravity. So for n equal 8, the group is SU4. For the other case, it's just U. n/2. It's just a condensed way to write it. Yes, actually, sorry, I'm not seeing the chart. If you can just tell me if there are questions. Thank you. Okay, so I have an example. Maybe since I'm already off through the talk, let me very briefly just to sketch how this works. So this is a very well-known setup. Is it known to be not scale separated? In fact, as far as I know, there are no proposals with scale separation in 4D n equal to 2 supergravity, as far as I know. This one known model, which has an M-theory origin, so M-theory on Sacking-Einstein 7 manifolds, gives 4-dimensional equal to 2 gauge supergravity. So the setup I talked about before. The part of the model I'm interested in is captured by one single function of the scalar fields. I have two scalars, x0 and x1. Actually, I have only one scalar, but okay, let's not enter in this detail. Just the point is that if you give me this function, I can compute half of the Lagrangian, basically, what is called the vector multiplet part. I can compute it completely. There is another part which I need to compute, which is associated to the scalar potential. And I need a bit more information. I need to know which isometries of the scalar manifold are gauged to do it, but this is known how to do it in this very simple case. Bottom line, I can compute anything I would like to compute in this model. I can do it very precisely. I know which groups are gauged. There is a U1 times U1 group, which is gauged on the vacuum, on the supersymmetric anti-de Sitter vacuum. It survives a U1 R symmetry factor of the full gauge group. So this is a situation in which I can really apply the weak gravity conjecture. Now, if you're familiar with gauge supergravity, I'm putting here some more information, like how the gauge charges appear and so on, but it's not really important. Eventually, you can do the computation. You can compute the vacuum energy. You will find that I didn't write it here, so you have to believe me. If you compute it in some units, this will be minus 12. Okay, the vacuum energy in some units, the ADS will be minus 12. However, if you do it properly, you recognize what is the gauge group and what is the gauge coupling, you will see that minus 12 is basically minus 6 times the gauge coupling square, okay, in some units. It means that the vacuum energy is of the same order as the gauge coupling. It means that, again, I am in this situation here on the nose, basically, without doing anything else. The only way to evade this situation would be to have an additional parameter here. Let me call it, I don't know, P or Q, whatever. And then I can play with this additional parameter and try to decouple the vacuum energy from the gauge coupling. This is not the case for this vacuum, and we claim this is not the case in general for supersymmetric ADS vacuum, according to this argument. There is no other parameter entering the vacuum energy. It means you cannot decouple the vacuum energy from the gauge coupling. And if the gauge coupling is the cutoff, you cannot decouple the vacuum energy from the cutoff. So there is no scale separation in this model. So this is possibly pointing towards a more general lesson. So what I showed you is that supergravity, local supersymmetry plus weak gravity conjecture is telling us something about scale separation. And if you're familiar with the Swampland program, scale separation is somehow addressed by another conjecture, which is called ADC, anti-de Sitter distance conjecture. So this is very much related to scale separation. So what I showed you in Insight is that supergravity plus weak gravity conjecture is somehow telling me something about supergravity plus anti-de Sitter distance conjecture. So possibly we propose that this could be a general fact that supergravity plus some input, some external input, is powerful enough to find new properties of quantum gravity. So new, if you like, new conjecture or new quantum gravity principles. Anyway, let me now go back to the problem of scale separation in this model. So how can we extend this? In the papers, we give explicit arguments. So a proper derivation in 4D and 5D, n equal to 2 and n equal 8 supergravity. So the maximal supergravity and the minimal with at least 8 supercharges. We believe that there is no obstruction in promoting the argument in the between from 8 to 32 supercharges. We don't see any obstruction. So it means that from 8 to 32 supercharges, there should be no scale separated anti-de Sitter vacuum because the argument I presented should be valid as well. Then you can ask, what are the corners which are not covered by the general argument I gave you? This is models with very little or no supersymmetry with at most 4 supercharges. This means for the n equal to 1, supergravity or n equals 0, or for example 3D n equal to 2 or less, or possibly also two-dimensional models, and I will talk about them later. Interestingly, the only proposals, as far as I know, of scale-separated vacuum from string theory, from string compactifications, or from top-down, are precisely in these corners, okay? So there is, these are two completely different lines of research, bottom-up and top-down, but they are still very much compatible. So there is no clear clash between these two reasonings. Now, let me, before talking about concrete top-down models, which is the second part of the talk, let me briefly say something about two dimensions. Now, in less than 4 dimensions, we know that gravity behaves differently, okay, than higher dimensions. In particular, we expect that fundamental principles of quantum gravity, like the weak gravity conjecture, might be different. Still, it's a fair question, is why, if there are scale-separated vacua in 2 dimensions, for example, why not? It's a fair question at theoretical level, at least. It's maybe not phenomenologically interesting, but still, at theoretical level, we want to understand all the possibilities. What we observed is that despite systematic searches, like, for example, this paper, which served really as a motivation for us, there seems to be no proposal for a string compactification down to 2 dimensions having scale separation. Okay, just scale separation. I'm not asking for anything more. So the question is, can we then explain this again with an argument from bottom up, at least in some cases? And since gravity is behaving differently in 2D with respect to 4D, we expect this argument to be really specific to 2 dimensions. So this is the topic of a recent paper last year with Fotis Farakons and Niccolò Cribiori. And I'm here sketching the argument, okay? I think it's nice to present the argument in generic dimensions, so D, generic D, and then you will see why D equal to is special. So let us focus on ADS-D flux vacuum. What does it mean? It means that the vacuum energy is purely given by some square of some flux field strength, so some gauge field strength. If you are familiar with flux compactifications in string theory, this is the typical case, okay? The vacuum energy is supported by some, what is called a flux, is some generalization of the electromagnetic field strength, okay? Now, this is my assumption, okay? If the vacuum is not of this kind, I cannot say anything. But in string compactification, this situation happens quite often. So this argument applies to string compactifications. Now, we assume we need another assumption so that we have different vacua of this kind, and they are interpolated by a domain wall, okay? In 2D, the domain wall will be a particle, for example, and it's separating 2 vacua with different values of the cosmological constant. We ask this domain wall to be BPS, means it preserves some supersymmetry, because we want the 2 vacua interpolated on one side and the other of the domain wall to be supersymmetric. Because I need supersymmetry to run the argument. This is a technical reason. Under these assumptions, then I can write a sequence of inequalities, basically imposing this inequality. So the fact that the tension of the domain wall is an upper bound on the ultraviolet cutoff, morally, along with the same logic as the weak gravity conjecture, so an upper bound on the ultraviolet cutoff, and derive a relation of this kind, okay, between the ultraviolet cutoff and the typical scale of the vacuum energy, the Hubble scale. In principle, for generic dimensions, this relation is not telling me anything about scale separation, okay? I can have scale separation and still be compatible with this relation. There is no problem. However, if I put d equal 2, you see what happens. This factor goes to 1, and I obtain 1 bigger than lambda UV times LH. Once more, this is contradicting the relation I was talking about since the very beginning. So this relation needs for a good effective field theory. So only in 2 dimensions, this argument with a domain wall interpolating between ADS flux vacua is telling me something about scale separation. It's telling me that these vacua are not scale separated, if they exist in this form, at least. And indeed, we could explain now why all of the models studied from string theory in this paper are not scale separated. We could give an explanation from bottom up, because precisely this mechanism happens. There is a domain wall interpolating them, which is providing me with a tension, which is provided with a bound on an upper bound on the ultraviolet cutoff, which is incompatible with scale separation. Okay, since I'm already through quite some time, talking since quite some time, let me skip this. Maybe just trust me that it works. Here we present an example in detail. We tell you what is the domain wall for this particular model. In this paper, there are other models, and in all of the cases, you can show that the argument works. In fact, here is a general recipe for in flux quantization, how to understand, how to recognize the tension of this domain wall, and then to see immediately that there cannot be scale separation. So this concludes the first part, where I was arguing from bottom up for the absence of scale separation. Okay, so I was trying to constrain in the parameter space of all possible consistent effective field theories of quantum gravity. I was trying to rule out regions of the parameter space where scale separation is not possible, because it's in contradiction with principles of quantum gravity, which are believed to be true, like weak gravity conjunction. In the second part, instead, I will be more on the positive side. I will try to construct or aim for constructing solutions of string theory with scale separation. Are there questions in general for, on the first part?
Can I ask something?
Yes.
So in low-dimensional holography settings, there are typically some chaotic aspects going on. Is there any relevance to the discussion of scale separation for these aspects of low-dimensional gravity? Or is there
good question.
No apparent relation?
Well, the honest answer is that I don't know. I don't have an immediate answer to this. Indeed, lower dimensional gravity is different, and there could be maybe aspects related to that. I just didn't investigate, so I don't know immediately. I would have to think about it. But indeed, what I was trying to stress is that lower dimensions are different than 4 dimensions and 5 and 6 and so on. So if we are able to say anything about gravity in those dimensions, it will be likely using different arguments. So there might be new effects might be happening indeed. Yes. Other questions? Okay. Let me then go to this more positive part, if you like. So here I will try to be as simple as possible, but I think it becomes a bit more technical. Please interrupt me or ask me if there is something which is not clear. I will try to explain, at least in the most basic way I can, the various ingredients, okay? I will start from one of the most famous examples for a scale-separated vacuum in string theory. This is called DGKT after the authors who proposed it in this paper, even though there are earlier works on which this paper is built. So this is a string compactification, okay? Is an honest example. Well, supposedly should be an honest example of what is a string compactification. So it means there is a 10-dimensional space with a 4-dimensional part and a 6-dimensional part, okay? The 4-dimensional part will be a supersymmetric anti-de Sitter vacuum with n equal 1 supersymmetry, not realistic, but still the problem is about scale separation. So we are one step before asking about a realistic vacuum. We want just to understand if scale separation is possible in any form or any manner. The compact part is, I call it here an SU3 structure manifold to be as general as I can, but you can think of this like Calabi-Yau or even toroidal orbifold. I mean, if you're familiar with the term Calabi-Yau, just Calabi-Yau is correct. You can think of Calabi-Yau. So it's just not just this manifold, but there is another ingredient which are O6 planes. So in string theory, we have strings for sure. Then we have branes, like D branes. And then we have other objects. Among the most used objects, even though they are not very well understood, are O-planes. You can think of O-planes like somehow D branes, which are, however, stuck in some point in space-time. They don't move. D branes are dynamical objects. They can move. O-planes, they cannot move. Still, O-planes are needed in several situations because they give a negative tension. They have negative tension, so they give some contribution to the vacuum energy, which can help, for example, in finding the Sitter possibly, or scale separation, possibly. So this is the reason, the practical reason why there are O planes in this setup. Also, they break supersymmetry. So with just Calabi-Yau, I would have for D n equal to 2 supergravity. With O planes, I land on for D n equal 1 supergravity. And okay, the other term is M2A, it means massive type 2A. Okay, type 2A comes with a deformation, which is called the Roma's mass, and this deformation is turned on in this setup, and is actually important for this model. Now, this model is famous because of 3 properties which happens all at once, which are very rare individually, so it's even more rare to have them all at once. So this model has a 3 parameter, so it's really a 1 parameter family of vacua. This parameter is like the integral of a 4-form flux. So this is like a generalization of the Maxwell field with 4 legs instead of 2 legs. The integral is like charge, if you like, some sort of charge. And for each value of n, I have a different vacuum in this model. But as n goes to infinity, so as I'm going to large charge, I cannot go to small n because there is some flux quantization again to be implemented. So I cannot really turn n to be 10 to the minus 2 or 10, I don't know, some very small number. This is not possible. We'll be violating our construction, but n large is in principle possible in this setup, at least. When you take n large, you reach at the same time what is called large volume regime, weak coupling regime, and scale separation. What does this mean? Volume, it refers to the volume of the compact manifold, so the typical size of the compact manifold. This is large, and this is large with respect to the string scale. So this is addressing one of the problems I was mentioning at the beginning, that the manifold must, in any case, must be larger than the string scale to avoid corrections, to avoid worrying about corrections, string corrections. A similar thing for the string coupling. So for the string coupling, I need to be at weak coupling because then I can trust string perturbation theory. I don't have to understand very well non-perturbative effects in the string coupling and possibly corrections. So these 2 properties are needed to have a good low energy approximation in terms of supergravity. And what is remarkable is that with the same limit, I also get a parametric scale separation. This ratio becomes very, very small as n increases because of the negative power. Still, this problem, this setup had, let's say, problems or weak points, or some things which are not well understood and people were trying to understand. One of these is this massive deformation I was talking about. So the Roma's mass is called F0 sometimes, okay? Whenever this is turned on, people might complain, for example, this is a technical discussion, but just to give you an understanding, what happens when you turn on a Roma's mass is not clear anymore how to relate type 2A supergravity to M theory, and why you need to do so, because in M theory, what happens to orientifold plane is well understood, while in supergravity is not so much understood. So the hope is to understand better orientifold in M theory, basically. But this cannot be done in this model. Okay, this way is not feasible. Another related problem is that this model, this solution, this DGKT solution is found with approximations, okay? Because again of orientifold plane. The moment I have these objects, I'm introducing singularities in the supergravity equations of motion, which are represented by delta functions. To solve really these equations of motion, I need an approximation which is poorly, I would say, poorly understood, at least which was poorly understood up to recent years, which is called smearing, okay? You replace the delta function, which are singular object, with some constant uniform function, this distribution. And then you can solve Bianchi identities equations of motion. This might be physical for deep brains because this step physically is like saying, okay, I have a small compact internal space with deep brains which are moving inside. If the manifold is small and I'm very far away, I don't really see where the deep brains are, so I can average over their position. This is basically the logic. O-planes, though, are not moving, they are stuck. So this idea of averaging over their position is not really well justified. Still, it was the only way to proceed. And there are also several concerns about the holographic dual. I will not talk about this, but this is another problem. What we showed 4 years ago is that the first and the second problem, there is hope that they can be solved. okay? So we were able to improve on this model. So this would be in principle good news for scale separation. For example, the first problem was already known to be how to solve it, at least in principle, but we implemented it completely by using dualities in string theory. Okay, there are, for example, T dualities, S dualities as the most famous examples. It's known that using one of these dualities, in particular T duality, in the appropriate way, you can get rid of the Roma's mass. The price you have to pay is that you introduce other fluxes. Okay, you just shift a bit the ingredients. So you erase one kind of flux and you trade it for other fluxes. This was, I think, known. What is really the novel part of our work is that we use a new strategy proposed in these works to go beyond this smearing, this mirrored approximation for the orientiforms. The strategy is basically to set up a perturbation theory and understand the first, at least starting understanding the first order correction beyond the smeared approximation. So if I have smeared approximation, which is a constant distribution, then the constant minus the will be delta function is like a first order correction. This is a very systematic way to do it. And in this way, which I don't have time to explain, but in this way, we were able to show, at least at first order in this perturbation theory, that the solution was well behaved, okay? How this could fail? It could fail because you set up the expansion, you have to solve equations of motion order by order in the perturbation. Sorry, I forgot to say, the perturbation is in a small parameter, which is basically the same n as before, okay? So this strategy worked because in this model I have a naturally large parameter and its inverse is a naturally small parameter. So this is a good parameter to set up a perturbation theory. You do it for every field in your model, so the metric, dilaton, and so on, all the Ramon-Ramon fields, and you solve equations of motion and Bianchi identity order by order. We did this at first order in perturbation, and we found a solution. This could have failed because it could have been that already at first order, equations of motion could not have been solved. Maybe there could be an obstruction in solving them. In that case, probably we would have concluded that the smearing approximation was not justified, was somehow introducing consistency. This is not the case, but you understand that this is not even the end of the story because I just did the first order and one should go to possibly higher order to see what happens. But this becomes technically much more involved and we didn't do it yet. Okay, here I have some details on the setup. Maybe I will skip this. Basically, I just give you the result is that we find indeed that scale separation is possible in this new class of models in type 2A. These are details of the setup, so let's not talk about this. What I still would like to talk about this aspect of the construction, which I think is nice, is that after this 2T duality, we don't have the Roma's mass anymore. So in principle, we can understand the solution in M theory, so 11-dimensional supergravity. And indeed, it seems that a first non-trivial check was passed by the construction. So what happens is that in the smeared approximation, without Roma's mass, you can calculate the Ricci scalar of the internal manifold. This will be now a 7-dimensional manifold if you add a circle for M theory, okay? What you find in the smeared approximation is that the Ricci scalar of the 7-dimensional internal manifold is negative. However, if you solve equations of motion directly in 11 dimensions, so what I'm doing here is going from 10D to 11D by adding a circle. If I just start from 11 dimensions, I find that the Ricci scalar must be positive. So the only hope is that this mismatch is due to the smeared approximation, because I find this in the smeared approximation in 10 dimensions, and I'm adding the circle by hand. And this turns out to be the case, at least at first order in the perturbation theory I talked to you about before. We calculated the corrections to the smeared approximation, and we showed that they are enough to flip the sign of the Ricci scalar of the internal manifold. This is a first non-trivial check that there could be a scale-separated solution in M theory, so what will be the non-perturbative version of string theory. And okay, this by no means is setting the problem of scale separation, just a first non-trivial check. Doesn't prove the existence of the solution, but it's still, I think it's a good starting point to looking for scale separation in M theory. And this would be a much cleaner setup than the first model I talked about, again, because of the absence of Roman's mass and because possibly orientifold singularity should become what is called, should geometrize it, so it should become much cleaner to understand in the empty set. Okay, so very last thing I'll talk about is scale separation now away from vacua. So up to now, I reviewed and talked about scale separation on really vacua of your theory, so minima of a scalar potential, especially vacua, maximal symmetric vacua with supersymmetry. Okay, it's not clear if we live in a vacuum. First of all, for sure, we don't live in a supersymmetric vacuum, but it's not even clear if we live in a vacuum or if you are somehow slowly rolling down a potential. It's a fact that typically string theory solutions are in region of parametric control, so what is called asymptotic regions of the modular space are rolling solutions. So this motivates, at least conceptually, to look for scale separation away from vacuum. Okay. Why this is important or interesting theoretically? Because there are many no-goes for scale separation. So a situation in which you can exclude the presence of scale separation in string theory, but those are based on the assumption of being in a vacuum. Okay, going away from vacuum is a way to evade these no-goes. For example, this paper argue for the absence of scale separation unless you introduce orientifold. This is why all the construction I showed you before had orientifold. This will be a way to avoid some no-goes. Now, and let me review one of these no-goes, in fact, the one I talked about in one moment ago. So the assumptions are that we are considering string compactifications to 4 dimensions with some possibly well-understood ingredients like fluxes, Ramon and NS fluxes, some wrapped D-branes. Okay, these are just D-branes, meaning they contribute positively here, and possibly a term from the curvature of the internal manifold. Okay, there is a 6D internal manifold, which is compact, and then there is a 4D external space, a 4-dimensional theory with this scalar potential. This, in general, what happens in a string compactification. Now, you can calculate the ratio of the Hubble scale given by this guy, basically the square root of this guy, and the Kaluza-Klein scale. Under these assumptions that all of the D-brane terms contribute positively, meaning these are actual brane with positive tension, not all planes with negative tension, that the Kaluza-Klein scale is related to the last term. You might say this somehow ad hoc, true, but it happens to be a true thing in large classes of models. It's actually hard to evade this situation. Somehow, at least I personally don't really understand very well why, but this assumption that the Kaluza-Klein scale is given by the curvature part of the scalar potential in 4 dimensions is mostly true in many models. And then the other assumption that we use the fact that we're in a vacuum, so the first derivative of the scalar potential vanishes. If you do so, after a small calculation, you find that the ratio is upper bounded by a number. So this thing can never be parametrically decoupled. The Hubble scale and the Kaluza-Klein scale cannot be parametrically decoupled. What are the ways out are to relax assumptions. So one way is to relax the first assumption, meaning introduce orientifold. So you flip this sign now, at least for some guys. The other way is to relax this assumption. As I was saying, this is actually not easy. It happens to be true for the model I talked about before, the T-dual version of the GKT. We checked that this assumption is indeed relaxed. The third assumption, which I'm going to talk about, is to relax the other one. So relax the fact that we are on a vacuum. So we consider 4-dimensional models of gravity plus one scalar field in principle. And these are like cosmological solutions, because now we are away from a vacuum, so there is a notion of time evolving. And these are well studied. There are many papers. I'm not actually citing here, just reporting one of these, which I find particularly clear, but there are many. This is not the first paper on the topic for sure. There are many papers before this. There are 2 classes of solution depending on so these are Flimmer, Ramel, Romesu, Walker kind of cosmology, if you like, with spatial curvature K. I'm looking when I have a flat or negatively curved case. And the solution are known. These are 4 for the models of gravity plus scalar fields with some parameters. Okay, for example, lambda is the slope of this exponentially decreasing potential, small lambda, is a parameter. However, for certain values of these parameters of lambda and k, this can be a solution of M theory or string theory. For example, for these values, lambda squared equals 14 and k equals 0 or minus 1, this is M theory on a 7 torus with G7 plus, okay? This is purely classical. There are no Oriental, so it's like really a classical solution. But is it a good four-dimensional solution, or the solution is seeing the whole of the 11-dimensional space? This can be checked, and this what was one of the main points of our paper, is to check for scale separation in rolling solution, just as a matter of facts, as just in a very brutal way also, if you like. So in the first approximation, yes, I think it's a good word. You can estimate the Hubble scale for a cosmological solution and the Kaluza-Klein scale from the volume of the internal manifold, and you can check indeed that the solution is scale separated. Actually, the scale separation now depends on time. So this thing becomes more and more scale separated as time increases, because the power is negative. You can calculate the power from these numbers. Is negative. So the more you go in the future in time, the more the solution will look like four-dimensional. Okay, this one setup, you might say, so you were lucky, you found one setup, but what we find is that this actually seems to be quite generic, or at least more generic than on vacua. Okay, on vacua is very, very hard to construct a sample with scale separation. Away from vacua seems to be easier. For example, in type 2, on 6-dimensional Ricci flat compact manifold with some flux, the potential is similar again. The value of the parameter now will change because it depends on the flux number here. This can be computed. I'm just reporting the results here for various values of the internal flux. You can check that, again, the ratio of the Kaluza-Klein scale over the Hubble scale becomes parametrically decoupled as time increases. So P, the value of P is reported here, is always negative in all of these examples. So these are full class of models. It's not just one single model. The GKT will be one column here only, basically, conceptually. This is a full thing here. There are more models here than the one I showed you before on vacua. So this perhaps is pointing towards a general lesson. We don't know for sure, but I think we think it's interesting at least to look into this direction, namely the fact that rolling solutions for scale separation might be intrinsically different than vacua, and scale separation might be more easily obtained in rolling solution. This would be actually not bad news if it turns out that we don't live in a vacuum, for example. A general lesson we could point out, though, is that whenever your scalar potential has a term generated by curvature, so what I was calling R6 here, so whenever this term is turned on, then it seems that you don't have scale separation. We don't have a proof in all the examples we look at. This was this term was problematic for scale separation. It is an observation, it's a general observation we made. But if you, for example, have a Ricci flat manifold, this guy will be 0, so you can hope to have then scale separation. Okay, so to conclude, scale separation is a minimal requirement for phenomenology in theory with extra dimensions like string theory, and it is an hierarchy problem in our universe. And as any other hierarchy problem, I think it's very hard to understand, to address. Nevertheless, I think it's important to say that in recent years, there have been remarkable progress along two complementary directions, which I tried to review in this talk. In the first direction, in the first part, I was putting constraints on bottom-up models using properties which are believed to be true in quantum gravity, like weak gravity conjecture. In some cases, these properties are strong enough to rule out scale separation in the vast majority of the parameter space of your low-dimensional effective field theories. Still, there are corners which are not covered. So this is why research is important. The second part of the talk was following the other strategies, so to try to construct new top-down models with scale separation. I think it's remarkable to notice that before 2020, only basically one kind of model was available in the market, which is the model I reviewed at the beginning, so DGKT. Today, I think there was remarkable progress because at least order 10 models have been proposed. And these are really vacua, supposedly. These are proposals for vacua in string theory with scale separation in 3 dimensions and 4-dimensional antecedent. Also, as I said in the last part of the talk, I think it could be promising to also look beyond vacua, which has not been explored so much for what concerns scale separation. And I think that in this period, in this time, several questions about scale separation, thanks to recent progress, are likely within reach. So I think this is a very interesting time for this open problem in string compactifications. So thank you for your attention.
Thank you, Niccolò, for this very interesting talk. Are there any questions from the audience? We can stop the recording and then